So this is an introduction to many body physics with slides made by Robert van Leeuwen of the University of Yavaskla and with a voiceover by Deepak Ved. So we will start with the very basics of quantum mechanics, Hilbert spaces, vectors, time evolution given by the Schrodinger equation, and so on. So you can see in this slide that a state is can be written as a superposition of these basis states, which here is shown as ket vector n, and these basis states we will assume that they form an orthonormal basis, and the psi of n component of the state psi can be expressed by taking the inner product of the state with the basis component. So this also gives us what is known as a resolution of identity, which is the statement that if you take the basis states and sum over them in this manner, you get the identity operator acting on your Hilbert space. So just to be clear, this quantity here, which looks like a ket followed by a bra, is actually an operator, and whenever you have something like this, it acts. So let's say you have some state phi and some other state psi, and this quantity is an operator, and the way it acts on any other state is you take a ket, let's say chi, and you put it on the right. So now you have the inner product of chi and psi which is a complex number in general, multiplying the state phi. So you get a map from the Hilbert space to the same Hilbert space. So that makes this an operator. Now the time evolution of a quantum state, as usual, is given by the Schrodinger equation. So you have the time derivative, the Hamiltonian operator acting on the state. We set psi naught to be the state at some initial time t naught, and now in order to solve it, we need to know how to write down this Hamiltonian operator in a given basis. So to do that, what we do is we calculate the matrix elements of this operator, and we do that by sandwiching it between two different basis states, here shown as n and m. So now the next step is the following. We take the Schrodinger equation and we put a ket to the left. So we have this psi state, and we act on the left with a ket n, and since this state is taken to be time independent, we can move it through the derivative. So the same state has to act on the right hand side also, so we have to put a ket over there, and now we use the resolution of identity which was shown in the previous slide, and we insert an identity operator here between this Hamiltonian and the state psi. So now what happens is you can see that the Hamiltonian is sandwiched between two states n and m, and so instead of this expression we can write down the matrix element h and m, and this combination basically gives us the component of the state psi along the mth vector at a given time t. And so as a result, the Schrodinger equation can now be written in this form, which is the time derivative of c of t, where c of t is the projection of psi of t on the nth basis state, and that is equal to h of t acting on C of t. What is h of t? H of t is this matrix H and M acting on C. So C is basically a vector whose components are these psi of n t, with n going from 1 to however many dimensions there are, whatever the size of the Hilbert space is. So as an example, we can look at states in the so-called position basis, and we say that, let's say that you have some real line over here, and a particle can be found to be at any given interval, let's say x, between x and x plus delta x, or we can write that as between at this interval, as we can write that as corresponding to x of n. So for example, this is x of n, this interval is x of n plus 1, this interval is x of n minus 1, and so on. And we say that these are our orthonormal eigenstates, and so they satisfy the usual condition and they form a complete set. So that means you can write down a resolution of identity in terms of these states. And of course that is true, because if you have a particle in one dimension, that is, let's say this is a finite box, or it can be the entire line, so the particle has to lie somewhere inside this box or somewhere on this line. So that's basically what this resolution of identity is saying, right? That probability of the particle lying somewhere on this line, when you sum it over the all of the states, that should give you 1. And now if the system is in a certain state psi, then the probability to measure a given state x of n, what is that probability? So now psi is written in this manner. So this can be written as summation of psi of n times x of n. So the particle is in a superposition of different position states, where the amplitude of each position is psi of n, and the corresponding probability is psi of n amplitude square, which is shown over here. The probability is the norm of psi of n, which is psi times psi star. So that's a real number, and that's what we want probabilities to be. So now for this system, we define a Hamiltonian, and we say that so this is the Hamiltonian operator, H with a hat, and again, as usual, we sandwich it between two different position eigenstates, x and x prime, and we say that the resulting matrix element of this Hamiltonian operator is given by this expression, where the first term is, as usual, what is understood to be the kinetic energy, and the second term is the potential energy. So this is nothing more than your usual minus h bar squared 2 by 2, and this kind of an expression acting on psi of x. So now again we look at the Schrodinger equation. So this is the Schrodinger equation, and this is I d by dt. And now you have to be careful, you have to see that here I d by dt it's not acting on the state psi, it's not acting on the state psi, instead it's acting on the component of the state psi of xt, and this component, as you can see, is given by this expression. So again, the right side, we have to put the x ket on the left. When we do that, again we introduce a resolution of the identity. Now here there's a small change from the previous slide. In the previous slide, we took our position eigenstates to have some finite width. So we have a discrete set of states, and our sums over all of the states are given in terms of ordinary sums rather than integrals. Here, Leuven has switched over to the continuous representation, and so now instead of a sum, what you have is an integral here. And so you have integral of dx prime, x prime, x prime. This becomes your resolution of the identity. So this operator is inserted here between h and psi, and once again you get the matrix element, and then x prime and x prime is going to be nothing more than delta x prime, and when you integrate this over dx prime, you'll just be left with this expression at the end. So this is again nothing more than the Schrodinger equation. The left hand side is tells you that the time derivative is given by the total Hamiltonian operator acting on your state. So now we come to the first step towards many body physics, which is two particles. So let's say again we have two particles now. So here they are shown these particles, they are living in a plane, they are living on a one-dimensional line, but there are two of them. And so these two axes, this axis over here and this axis over here, they both represent the same real line, but we have two different axes to illustrate the fact that we have two different particles. So the combined state of the system can be written in this way. So what this is what is known as a tensor product state. And now these particles, let's say that they are indistinguishable. So if they are indistinguishable, then what that means is that if I exchange the two particles, if I exchange their positions, so this is particle A, particle B, and then I move them so that B takes over A's position and A takes over B's position, then the resulting state can be written as x of m, x of n. And if these two particles are indistinguishable, then the new state should have exactly the same probability as the first state. So in other words, if I take the amplitude of the first state, which is this, it should be equal to the amplitude of the second state, which for lack of space I'd write over here, which is lambda square xm xn xm xn. And now since all of these states are normalized, that means this is equal to 1 and this is equal to 1. So that tells me that lambda square is equal to plus 1, but that means lambda can be equal to plus or minus 1. Now depending on the value of lambda, one has either bosonic or fermionic statistics. So if lambda is positive, that means the phase of the system does not change under particle exchange. Then you have bosonic statistics, which corresponds to the positive sign in this expression. Otherwise, you have fermionic statistics for a phase change of -1, which corresponds to the negative sign here. So if you want to write down a system which is invariant under such particle exchanges, there are two ways to do that. So if one has a bosonic system, let's say consisting of two particles, so we would write this system as x1 x2, so which is x1 tensor x2. Now under particle exchange, a bosonic system should be symmetric, that it should not change. So how do we write down such a state? Well, we take x1 x2 and x2 x1 and construct a superposition of these two states. and this is a symmetric or bosonic uh, state. If we make it an antisymmetric state by putting a minus sign, we get a fermionic state. So in general, if you have n particles, then there is a more compact way to write down this wave function. So this is the symmetric wave function, and this is the antisymmetric wave function. And the way to do that is via something called a Slater determinant. So basically, you write down in a matrix form all your single particle states. So as an example here, this is an illustration of a Slater determinant state. This is actually an inner product state, but if you want to write down a Slater determinant state, what we do is we put all of our n particles in a matrix of this form. So for instance, x1, x2 till xn, and then again x1, x2, xn, and then we repeat that n times. So this gives us a state, this gives us a matrix which is n by n in size. So it's n by n matrix. And then we take the determinant of this matrix. So as an example, let me work out the determinant of 3 by 3 matrix of this form. So this determinant, you can see, will be x1, x2, x3 minus x1, x3, x2, x2, x3, x1 minus x2, x1, x3, x1, x2 minus x3, x2, x1. So where each one of these terms is a tensor product state. So x1, x2, x3 is actually the state x1 tensor x2 tensor x3. It's a 3 particle state. And now you can see that taking this determinant has given me a superposition of all these states with the particles exchanged with each other, and whenever there is a even permutation, I get a positive sign, and whenever there is an odd permutation, I get a negative sign. So this is the asymmetrics or the fermionic state for 3 particles. Now I can use the same technique to write down the symmetric or bosonic state. The only difference is that instead of taking the usual determinant, what I do is I take a so-called symmetric determinant. So I'm sure that there is some official terminology for this, but this is my own phrase. So the symmetric determinant, for instance, of a 2 by 2 matrix would be x1, x2 plus x2, x1. So it's the same as the usual determinant, only instead of a negative sign, wherever you have a negative sign, you put a positive sign. So you can see that quite simply that if you take this so-called symmetric determinant, then you will get this symmetric state. So this is the bosonic state and the other is the fermionic state.